Hi, my name is Anthony. I'm in my 5th year mechatronics engineering. I've been on the team for 5 years and I've been working with UAV since high school. My current role is the team lead. I make sure everything runs well, and during the flight day I'll be handling the autonomous mission planning.
Hi, my name is Marco. I'm 3rd year aerospace engineering at UNSW and it's my 1st year on the Flight Labs team. I'm currently the ground station lead and business operations manager.
Hi, I'm Matthew. I'm in my 5th year at UNSW and it's my 4th year on this team. I do a lot of CNC work and my role on the team is in manufacturing, and at the competition I'll be doing assembly and repairs.
Hi, I'm Daniel. I'm in my 5th year of electrical engineering and I've been on the team for 4 years. I've been designing and building drones for 8. I'm the electrical team lead and the team pilot.
Hi, my name is Edward Thompson. This is my 4th year at uni. This is my 1st year on the team, but I've been interested in drones since the beginning of uni. I'm computer vision lead and I'll be watching the system on the flight lab.
Hi, my name is Luke. I'm a 2nd year mechatronic engineer. This is my 1st year on the team. I am the safety officer and also the UGV lead in charge of repair and manufacturing of the ground vehicle.
Hi, my name is Daniel and I'm a 3rd year aerospace student at UNSW. This is my 2nd year on the team. I'm the current structural lead and I work on designing, testing and manufacturing our aerospace structure in a drone.
Hi, my name is Ali and I'm in 4th year and I study mechatronics engineering. This is my 2nd year on the team and I work in conjunction with the electrical lead to design PCBs and implement UAV CAN. Also, I work on the assembly of our aircraft.
My name's Arfin and I'm the aerodynamics lead and safety pilot for the team. I was responsible for the design of the airframe, as well as at the competition I will be doing the safety checks.
Here's a quick system overview of REN. So all of REN's control electronics sit in the nose cone. Our companion computer handles our high-level control and does image recognition on board. The cube autopilot handles all of our low-level control. All of our components except for the telemetry radios communicate over UAV CAN, so we can reduce wiring and have a robust communication bus around the aircraft. For our software, we are running ROS on the companion computer. So ROS has our control nodes as well as computer vision nodes. We communicate to a ROS MAV-ROS node via MAV proxy. MAV proxy links up our mission planner, so that shows all our stats of the aircraft, and we have a dynamic mission planner that will autonomously develop paths and connect via MAV proxy to communicate to our system. Our upload node will transfer data to our analyzed image data section in our ground station, and that will get sent off to the interrupt system.
We will be attempting the competition within the 40 minutes. We are reasonably confident that we can achieve it in this time, but we'll be aiming for 30 minutes with no post-processing. The autonomous part of the mission, which we have already tested, we are therefore extremely confident that we can achieve this. The waypoint capture we will be attempting once, and we are fairly confident that we can achieve a high level of accuracy. The obstacle avoidance we'll be attempting because it is built into our flight software already. The object detection, we'll be doing the search area fully autonomously, and we are highly confident in this. The off-axis we'll be doing autonomously, but we are not as confident. And also the emergent object we'll be attempting manually, but we are highly confident with that. The airdrop we will be attempting and have planned and have tested, so therefore we are highly confident.
I'm at the James Kirby Makerspace at Mechanical Engineering at UNSW, and we have set up on the tables here a few samples, test units and prototypes that will kind of demonstrate our process from idea to validation to implementation. So first of all, we work a lot with composites, and that begins with producing core mold sections. And we typically do that on CNC machines such as router tables at the university, and once they've been machined, we lay up on top of those with a vacuum bagging method and 2-part epoxy with our composite. So here's an example positive layup section that was designed to demonstrate or mimic the kind of geometry we've been encountering in the fuselage. So it has like a kind of bay area and an airflow section, and as you can see, it turns out nice and strong. Can withstand a fair bit of abuse. Moving on, something else we wanted to try out with this build was incorporating 3D printed sections into our cores alongside that foam. So this was our first test there, where we used PLA filament and then laid fiberglass over it. And in the sections where there were cutouts for certain things in the internal areas, we had issues where the 3D print crushed under the vacuum forces. So that was due to the PLA being quite weak at the infill percentage it was at. So now we use PETG for those sections, and that works better. So this is the first prototype we built. It has a foam section for most of it in the middle here, and then 3D print sections for the wing areas. And this has been really, great for testing. It's really bulletproof, really strong, but it's too strong for a final entry. It survives some incredibly horrific crashes. And also for surviving crashes, we have these replaceable motor mounts that are designed to just snap at the joint with the tube. And so our motors and carbon booms and other expensive hardware are not damaged in crashes, and we can quickly get flying again. We've reduced, for our next iterations, the amount of 3D printed area down, because those 3D prints, despite being quite light, are still nowhere near as light as the foam. So we really need to bring that weight budget down in that regard. So moving on to the final kind of section here, we're going to look at our wings and the way the wings join to the aircraft. So here is our next iteration on our wings. It's a slightly different profile due to some center of mass issues we encountered with that first prototype. These sections are fresh off the mill, and they're in two halves, where on one side of one half we have internal features such as accommodation for spars and servos and wiring, and then we have the wing profile on the top. And so they get the internal parts put inside them, glued together, and then laid on top of to produce the final wing. Finally, we have some testing for the latches that hold this wing to the fuselage. So this was a depthing test. We have these 3D printed nylon catches where we played around a bit with how weak they were and how bendy they were. And this one, everything's a little bit tight, a little bit too good. As you can see, it kind of comes together all right, but it's a very tight snap, and it's very difficult to get apart. So we kind of loosen the tolerances there a little bit for our next prototype, which comes together more satisfyingly, more gently, and that pops in between the wing and the fuselage.
I have here some examples of the development testing we use to inform the design decisions behind the electrical systems of our aircraft. Now, most small drones typically use individual signal wires to control each component of the aircraft, but in a system of the complexity we were aiming for, this made wiring completely unmanageable. We looked into an S-bus system that runs multiple signals on a single servo wire. However, this was very prone to noise and interference, so we moved to testing a fully digital mesh network based on the CAN bus standard. This allows us to run individual nodes and reprogram them to do any task that we need, from running ESCs, servos, telemetry radios, or GPSs. This GPS magnetometer combo here has just demonstrated the bus can also be monitored in real time by this computer here. Now, the next thing we needed to work on was the batteries for our aircraft. Space is very limited in our airframe, so we had to make the batteries fit whatever space was available. We did this by configuring individual lithium polymer cells into whatever shapes we needed. The other limitation the airframe placed on us was that the parts of the airframe can be separated into separate modules. This meant that we needed a simple way of connecting the two parts together that was easy to use and reliable. The last part of the airframe we needed to test was the propulsion system. Now, in our experience, the data provided by the manufacturers of these small hobby-grade components tends to be fairly unreliable, so we needed to test it for ourselves. To that end, we sampled a variety of motors and different propeller types and used this thrust stand here behind me to analyze them. This allowed us to get data on the thrust, the performance, and the efficiency of the motors through a whole range of RPMs and in any combinations we needed. After analyzing this data, we were able to balance the cost of larger propellers and larger efficiency with the larger airframe that they require, and we ended up selecting the motor you see here and the smaller folding propellers in front of me.
The autonomous aspects of this mission will be handled by the onboard flight controller running AUVSI. The PID loops for REN were tuned in manual mode, after which the aggressiveness of the controls were also tuned. As these PIDs are used in the control loop for autonomous flight modes, no autonomous flights were undertaken before this tuning was completed. 8 autonomous flights have been conducted, with no manual flight in any of these tests. Initial autonomous flight tests involved a manual takeoff and landing, however these were obsolete after initial safety tests were completed. Throughout all autonomous flights, REN was able to hit all waypoints either within 15 or 30 feet depending on the mission. With a waypoint radius of 15 feet, some manoeuvres were quite extreme. However, these manoeuvres were considerably smoother when the waypoint radius was increased to 30 feet.
This introduced an issue which allowed REN to cut corners or overshoot the waypoint, but this is not expected to impact the mission as most turns will be smoothed using multiple waypoints. If required, the waypoint radius can be decreased for high accuracy flight.
As of yet, we have not integrated the obstacle avoidance code, so it has not been tested. Obstacle avoidance is built into our autopilot software, so we believe once we integrate it into our flight managing software, it will run as expected. For the image testing system, we printed our own markers and flew various cameras on a quadcopter at 100 feet and 165 feet and compared the results. We settled on the up camera as the images were the sharpest from our testing. From there, we tested the up camera in various conditions and speeds to see how it affected image quality. Here's a 2-scale mock-up of what the onboard camera sees. At 100 feet, we get an average resolution of 20 by 20 pixels. And at 165 feet, we get an average resolution of 9.6 by 9.6 pixels. The 100-foot image is the one we'll be transferring to the judges. Our strategy for the best image quality is as followed. We'll be using dual cameras, one facing down and one facing at 45 degrees. We've added cleaning lenses to our pre-flight checklist. We'll potentially remove the IR filter to improve sharpness in the camera. That's pending further testing. We will conduct at least 2 passovers, one at 165 feet and one at 100 feet. We will fly slow to reduce image blurriness. And image capture should only happen when the aircraft is flying flat and straight. We will turn the aircraft outside the image capture area.
For object detection and partial classification, we went out and took some footage and had people manually classify that data. Then we trained a neural network to spot objects on the data, and for here we will test the neural network to spot the images, and this is a unseen image, and here we can see there's shapes and people. This is a top-down view, and this is a horizontal view off axis. And here they will send the bounding box and the class to object detection and localization.
Alright, so here's our character recognition algorithm, which uses a neural network to get a bounding box around the character, and then it crops that image and feeds it into the algorithm that recognizes the character. See, it spits out YY. And here's our localization algorithm, which takes the field of view of the camera, the angle of the drone, the altitude of the drone, and the center pixel of the object to get the distance, and then it uses the bearing along with that distance to get the coordinate of the object. And here we can see that coordinate displayed on Google Maps 90 degrees from true north.
The airdrop mechanism for this competition is made up of an Arduino-controlled brushless motor, with a spindle attached capable of holding up to 165 feet of fishing line. From a height of 35 feet, 10 tests were attempted with the payload surviving all landings, landing an average distance of 5 inches from the target. Based on this testing, we believe the UGV will be able to land within 3 feet of the target from a height of 115 feet, accounting for linear error scaling due to drop height and a doubling of the error due to wind.
There are 2 types of testing the team is used to carry out full missions: live testing of the components in flight and software in the loop. Software in the loop is used to test the autonomous software and parameters to see if there are any bugs and to see how our aircraft will handle when we optimize it for speed and accuracy. SITL allows us to test experimental code safely and gives us the confidence that our autonomous system has no bugs that may bring down our aircraft. We have not been able to complete a full live mission test as of yet due to unforeseen circumstances such as the grounding of Q-Pilot's autopilots and access to airfields in Sydney. However, we've been completing basic live autonomous testing of the aircraft. We found things like center mass and control surfaces that needed to be adjusted, so we've taken these changes and applied it to our competition-ready airframe. We believe that through further testing, which is happening over the coming weeks, our system will complete the required tasks. Even though we haven't fully completed our full mission testing, this is a score we believe we will get based on our unit testing and simulations.